Welcome back, and in this video we're going to be looking at the second section of the notes. We're going to be looking at making polyesters and polyamides, and we're going to be looking at the amide link between amino acids. So we're on page 6 of your notes, and we're looking firstly at polyesters. Now these are called polyesters because they're a polymer, but they're joined together by this ester linkage. We have a dicarboxylic acid. In other words, we have a carboxylic acid with 2 carboxylic acid functional groups on each end of the molecule, and a dialcohol. And we lose, if you remember, the OH group from the carboxylic acid and the hydrogen from the alcohol. And we do that on both ends. And then we join them together to make the polyester. And there, sitting in the middle, is my ester linkage. The other way we can make a polyester is using a diacid chloride. So I've got a diacid chloride, and again I'm just going to use a dialcohol. And in this case I'm going to lose the chloro from my diacid chloride, and again I'm going to lose just the hydrogen from the alcohol group. This time, instead of making a molecule of water, I'm going to make a molecule of HCl. So the last way I need to know how to make a polyester is where I have my 2 functional groups, my OH functional group and my carboxylic acid functional group, on the same molecule. So if I look at 2-hydroxyethanoic acid, so I've got ethanoic acid, which has my double bond oxygen OH group, but it also has an OH on that second carbon. So I've got both my alcohol functional group and my carboxylic acid functional group. And again, what will happen is I will lose the hydrogen from the OH group, and I will lose this group here. And then I'm just going to draw out my repeating unit. So I've got my oxygen there joining on. I've got my carbon here with my 2 hydrogens. I've got this carbon with my double bond oxygen, and that's 1 repeating unit. If I repeat that, again starting with the oxygen, carbon with 2 hydrogens, carbon, double bond O, and again a line. Now if I put a bracket around that and an N, that's showing I've got 2 repeating units. If I was to pick that up and put it there, that would be fine, and it would be repeated down the polymer chain. Polyamides are made in a very similar way, only this time you have your dicarboxylic acid and a diamine. So again, from the carboxylic acid, I'm going to lose that OH group, same as I did with the polyesters, and I'm going to lose 1 of these hydrogens from these NH2 groups, so I become NH1. Then again, I join them together with the elimination of a small molecule of water, which is why they are called condensation polymers, to make that polyamide link. I can do exactly the same using the diacid chloride, only this time instead of eliminating a molecule of water, I eliminate a molecule of HCl. But I get the same polyamide with the same amide link. So we're going to practice drawing a few more of these. So I'm going to start this time with benzene 1,4-dicarboxylic acid and ethan 1,2-diol. You have to be careful on this one that you've got your carboxylic acid functional groups on the correct places around the ring. So this is carbon number 1, 2, 3, 4. And you need to be careful when you come to draw the polymer unit that you keep them at position 1 and 4. And here we've got the OH groups on separate carbons. So there I've drawn out 2 repeating units of this polymer, being careful to make sure that my carboxylic acid functional groups are on carbons number 1 and 4 of my benzene ring, and watching the terminal points as well, so I don't get a double oxygen bond. So I've got my C double bond O here, and that should link to the oxygen of the alcohol functional group. A classic mistake is to put a single bonded oxygen here and here, or a double bonded carbon somewhere as well. So do make sure that they are repeating units. And this is 2 repeating units, and I've got 2 ester linkages. So there's 1 ester link there, 2 ester linkages, 3 ester linkages, and then this one and this one would make a 4th ester linkage. So we also should be able to do this backwards. In other words, given the polymer, given a repeating unit as a polymer, we should be able to draw the monomer that it's come from. And that's very easy. All we're going to do is put the hydrogen back on the alcohol functional group and the OH back on the carboxylic acid functional group. You could also have here just have a chloro group, so this could be an acid chloride functional group instead. So we're on page 8 of your notes, and we're just looking at a few more examples. So here I have an example of a molecule with 2 acid chloride functional groups on it. Again, be careful of the position of these. It's a 1, 3. And it's going to give my polymer a little bit of a kink. I also have a diamine. And again, I'm going to make this amide link, here it is, between my 2 monomers to make a polyamide. I've just done 1 repeating unit of that. So this carbon here would be attached to the nitrogen here to make the amide link. And the last example on this page is Kevlar. So again, I've got a diol chloride and I've got a diamine. I'm going to join those together to again make a polyamide. So because the amino acid contains both the carboxylic acid functional group and the amine functional group, they can join together to make polymers of only 1 monomer units. So they can also join together to make proteins, which are made up of different amino acids, but those amino acids are joined together in exactly the same way. So I'm going to start with glycine, and I've got my carbon joined to my hydrogen. I've got my C of my carboxylic acid functional group, which has a double bond O in it, and it's lost the OH functional group. On the other end of the molecule, I have my nitrogen, which has lost one of its hydrogens, and again, it's formed a link to another amino acid. And that backbone is the same no matter what amino acid I am dealing with, because the only difference between amino acids is what the R group is on this carbon. So they're always going to have the same backbone, if you like. It's only this R group here which is going to change. Well, for glycine, it's just a hydrogen. For aniline, on the other hand, it's a CH3 group. So that's all I'm going to do for the rest of them, is I'm going to add in that R group. So for the last 3, all we've done is just add in the different R groups. So you'll notice the backbone stays the same. It is simply the R groups that change. And I've got there 1 repeating unit. So if I wanted to do 2, I would pick that up and repeat it there. So the last type of polymers that you need to be aware of is addition polymers, and these are polymers which contain a carbon-carbon double bond, and you will add across the carbon-carbon double bond. So you need to look out for the ene part of the name. So this is polypropene, En, amide, polypropene, oic acid, and polyethene, ol. That tells me that it's got a double bond in it. So there are my 3 examples of addition polymers. So they've got this double carbon-carbon bond, and that's what we're adding across, remember. So this group here becomes a group here hanging off the chain. Same with this one and this one. So you need to be careful that you're adding across that carbon-carbon double bond and nowhere else. Properties and uses, well, some of them can form very strong cross-linkages. They can form a water-absorbing gel. So these ones, for example, are used in soft contact lenses. These, again, can water absorb, and these OH groups have a high degree of hydrogen bonding. So they're actually, unusually for a polymer, very soluble in water. And this is what soluble fasteners and bags and liquid tap capsules are made out of. So we've come to the end of this topic now, and just looking back at the statements on the front cover, so you need to be able to do all of these things. So formation of polyamides and be able to make those polyamides and those polyesters, understanding the properties of those amino acids in terms of their acidity and basicity in solution and the formation of zwitterions, the fact that all of them, with the exception of glycine, are optically active, and looking at those peptide bonds in proteins when you get the amino acids forming or combining together by condensation reactions, and the fact that we can then hydrolyze those using concentrated acid into the constituent amino acids. Those then could be separated and analysed by thin layer chromatography. So that just finishes this video looking at the amino acids and polymers and proteins. So in the next video we're going to move on and look at benzene rings in the aromatics pack. But until then, take care, stay safe, speak to you soon. Bye bye.